Hello, I'm Marcos Guimarães. I'm here from the Lawrence Center, the workshop of quantum magnetic materials. I'm here today with Marcelo Lopes.
Hi.
Semonti Bhattacharyya.
Hello.
And Jose Hugo Garcia.
Hello.
And we are here today to talk about 2D magnetic materials, specifically about applications and the applications in spintronics. And maybe we could start already with a big question, right? Do you see 2D magnetic materials being applied in electronics in the coming year in the real world? So maybe who wants to start with that? Perhaps Semonti?
Yeah, I think at some point we will have to, because the whole electronics industry is shrinking, and that also requires shrinking of memories, and memories require magnet. So at some point we will have to find something that works in room temperature, and that can lead to the application of 2D magnets in electronics.
So, Jose?
Although you have to define like time scales, right? Do I see that in the forthcoming years? No way. I mean, we are far we need to learn more to actually be able to transform these new kind of materials into new technologies. But as Shimon say, I believe it's a good path that we should try to follow.
Yeah. Marcel?
Yeah, I think now we are in this phase of identifying materials that are promising for such applications, different ones, right? And I think we are all also aware that at certain point you have to start developing materials on a large scale, right? And that's what I'm trying to do and so on. But as Hugo said, it will not happen in 1 or 2 years. But I think we are in the right path, right?
Maybe not 10.
Yeah.
Not even 10.
Right.
Yeah, maybe
We're now in this
decades.
fundamental part. I think also people growing bulk crystals, they're still trying to grow better materials with higher prospects, for instance, high transition temperatures, but it takes time. But I think that it's nice to see here in this workshop that the community seems to be going the right direction, right? And there's a great interest, and more people are starting to look on these materials, right? Also people with a lot of background in spintronics, that's really important.
Yeah, and I think I agree with all of you, and I do agree that probably not 10 years from now. I think that would be too optimistic, but perhaps in the far future, after we solve some of the key challenges in the field, right? But since we have to solve these challenges, it would be nice to establish what the challenges are. Maybe Marcelo, we want to start with, in your opinion, what do you think are the key challenges now that hinder applications?
I would talk a bit from my point of view, right? So I'm a guy doing material science and trying to grow materials on a large scale. I use as a tool molecular beam epitaxy. Of course, one might argue molecular beam epitaxy, MBE, it's not the best technique because at the end, this is not really widely used in industries. At a certain point, you want to develop CVD processes, so chemical vapor deposition and so on. But still, I see as one key element is trying to, first, after identification of promising materials, that you should try to develop protocols for growing that on a wafer scale, right? What wafer scale means, of course. On an MBE, we are exploring usually 2-inch wafer size and things like that. But that's a good start, right? So you want to, it's not only growing and say, okay, we grow on a 2-inch wafer. There's a lot of basic studies that you have to do in terms of epitaxial growth. And this has to be developed right now. And this is key, right? Because at the end, even if you identify a great material with very high transition temperatures, you have to be able to synthesize these things on a large scale.
Jose, do you agree with that? I mean, you probably have something to add from the theory perspective as well.
I mean, from the theory perspective, for us it's simpler. No, we go and simulate and found many materials that could be great. I think so. In that sense, the prediction of 2D magnets, or at least materials that have magnetic properties, is not that hard. What is difficult is to predict their properties accurately. And also, for doing that, you need to invest a lot of efforts from the theoretical point of view. And to do that properly, there should be some kind of communication with experimentalists, because otherwise you will be like, we were joking here about making a 2D magnetic memory of uranium, because so you might end up researching on these kind of things. And then another challenge that is generic, at least from my research field, which is spin orbit torque memory. So memories that are being switched through spin orbit coupling interactions. It's that you want this memory to work on a table device, on a normal computer. You need them to have high TC, because you don't want to lose this information, and this is at the moment not possible, and it's one of the key challenges that we have for the 2D memories.
Yeah, I think I agree with both Marcelo and Joao that, of course, one of the limiting factor is the size, and the other limiting factor is the temperature. But along with that, many of these magnetic materials are extremely sensitive to air. So we also need to be able to protect them. But it just doesn't end there. I think even at the fundamental level, we do not understand a lot about them. A lot of our experiments are quite indirect. So although I myself do transport experiments, we need corroboration from different type of experiments to be able to completely understand these materials.
Yeah, and I think also one thing that I didn't see it mentioned is the integration with the current industry, right? I mean, if you want to jump in the boat of the CMOS technology, you have to be able to integrate with the silicon processes, and that I don't see it happening, at least in the near future. And hopefully some growers like Marcelo can push the field there towards this integration too, right?
Yeah, I think and I'm not an expert on, let's say, material integration inside a clean room in a fab, in a microelectronics fab. But, I guess this has to be taken into account. What elements are there inside this new 2D magnet that you are growing? Are they allowing you to use that on a clean room? And all these things have to be taken into account. But, it's always like step by step. Yeah. Theory is predicting materials. There are fundamental investigations, things that you are doing, Marcos. I'm trying to grow these materials. There will be a point then when another guy will come and say, okay, let's try to integrate that. What has to be done for integrating that on a clean room processing line? All these things have to be carefully discussed. And what Semonti just mentioned is that capping layers, right? Because they are not stable in air. How to deal with this problem? And what kind of capping layers do you use? If you want to build up heater structures, then you have to start thinking about growing 2D materials on top of each other. So there's so many challenges that we are just, starting to look at that now. Yeah.
And perhaps I have a question, which are actually two questions. What are the main unique functionalities of 2D magnets, or what can they offer that is very unique? And how can that contribute towards new devices? So Jose mentioned spin orbit torque devices, right? Do you see 2D magnets being integrated in these devices, and why would they be better than permalloy or cobalt and iron?
I mean, I can see two clear reasons. One is that many effects that you have in, let's say, in conventional metals, 3D metals, are driven by interfaces, no? And spin orbit torques, or at least part of half of the spin orbit torques, can come because of this interface, no? You can switch because of interfacial interactions. When you have a 3D system, a lot of the current goes into the bulk of the system, and only a fraction of this current will go through the interface. In a 2D system, then it's basically a interface. So all the current that you are passing through the material is actually converted into the work that you want it to be. In a memory, will be into the torque that will ultimately switch the magnet. And on top of that, something that is very interesting from the point of view of fundamental physics, but also in the point of view of engineering, is that in two-dimensional magnets and in two-dimensional van der Waals structures, so stacking of different two-dimensional material, is that you can actually play with the crystal symmetries of the system. Which is something that is very, very, very hard to do when you have to do it with conventional growth, because then you will have to control all the growth very precisely, while in 2D material you just stack and you can slide and you can twist. And this control over the symmetries open a whole new world for engineering different quantum mechanical interactions. So that's just, for me, two of the most unique things that I can see in 2D materials.
I see Semonti nodding. I think you clearly agree with Jose, right?
Yeah, I agree with Jose, but and there are many more. So as Jose said, that here the interface is the entire device, and that also opens us up to other things like gating. The way you can use an external gate to dynamically tune the magnetic properties in these materials, that was never done in case of 3D systems. And also then there is strain as well, as we have also seen in this workshop quite a lot. So I think that way these kind of workshops are very good, because people who are trying to tune these things from different perspectives can get together and probably agree on one particular approach or a combined approach that will give us something very useful.
Yeah, and I think we touched upon that in the episode we just recorded on the fundamentals, which is that one of the unique thing of these materials is that we can they interact quite heavily with the environment, meaning that they will respond strongly to light or gating or strain or proximity. So you can really combine these things, and that's something that's quite unique, right?
Yeah.
And I think that can be nicely exploited towards industrial applications too.
Right, and I think one point that you already mentioned, Semonti, is that, all is about downscaling, right? Making ultra compact devices. And for the case of magnetic memories, for instance, one of the things that you want to have is like this perpendicular magnetic anisotropy that in principle it's been shown that even for monolayers of different 2D magnets you can have. And this is not to achieve on conventional, I would say, metallic heater structures that people build, where they really have to grow very thin metallic layers, which is very challenging. So if you can really use two-dimensional heater structures combining 2D semiconductors and 2D magnets, I think it's a big deal in terms of downscaling devices.
And perhaps one thing, I'm not a grower, so I don't know much about the when you try to interface several different 3D materials. But I think one of the problems that the industry faces is also the intermixing between different materials, and I believe that this is also less problematic with the van der Waals systems.
It can be, not necessarily. Then, of course, it depends on what kind of structures do you wanna build. Most of these 2D magnets now that we are investigating in general, it seems that in terms of I would say temperatures that you have to have in your substrate, in your wafer, to grow them, you don't have very high temperatures like graphene or hexagonal bornite, right? So let me say, if you want to explore synthesis of such materials on top of substrates like graphene or 2D templates like graphene or bornite, right, that's definitely not problematic. On the other hand, still, what are the solutions there that we have to have in order to put a graphene or an HBN encapsulation layer on top of a TMDC or a 2D magnet based on tellurium or selenium? So there, it's where I see that we probably would have to come up with solutions that includes not only large area growth, but also high quality large area transfer, right? And or also what Hugo mentioned is that if you start controlling the symmetries in the system using like twisting of layers and everything, this is very hard, if not impossible, to achieve by direct growth, right? Epitaxial growth, yeah.
And I would like to come back a little bit on the unique functionalities of 2D magnets or 2D materials combined with 2D magnets, specifically for applications. Because we've been trying, a lot of the papers have been using tunneling magnetoresistance and things like that, which are conventional systems, right? But is there something, some device that you could imagine that is like, that's a clear case for bringing 2D magnets into the picture? And
I think one of the biggest limitations I see in traditional hard disk or traditional memories is that you need to physically move a magnet to write something, and then you need to again physically move another head to read something. But in case of 2D magnetic materials, the gating can do it. So maybe we can imagine a crossbar array sort of device with magnetic materials where we can read and write without anything moving, and that already saves a lot of energy. So
yeah, and that I think goes into the in line with the spin-orbit torque ideas, right?
I think, the 2D, because this podcast is for like young people, no? That it's for like scientists, and it's interesting to also say that establish what are the characteristics this 2D material have, because I think most of the application that they will probably have in the future, we are not be able to see it now. Mm. One thing that is now starting to be imagined is for this whole field of neuromorphic computing, where you can use the fact that this is a sheet, you can pattern it, and then you can create some kind of like artificial neural network, because it's a 2D. This is not only for the 2D magnet, but the 2D magnet has a natural way to do that via the nonlinear dynamics of the magnetization. So this is just one of the things. You have also correlation or effects that are maximized in this. So maybe you can use them to use gate to turn on and off a superconducting state, which is something that is impossible now. And then who knows what this could be useful for.
Yeah, well, I'm not an expert here. You can probably, Marcus, tell us more about that. But I think this idea of all optical control of magnetic properties, this is something I find fascinating, and then I don't think you can achieve in traditional magnetic materials, right?
Yeah, that's definitely true. I mean, the combination of photonics and magnetism is something that is quite unique, and might open a new avenue, right, for new type of devices. And I think also we mentioned before in the previous episode on the topological properties of these materials, which can also be explored, right, for towards new type of devices which actually dissipate less energy. I think that is another great opportunity for 2D magnets.
Right.
Yeah.
But now I have a final important question. If we had to convince one of the big players in the field, so Intel, Samsung, TSMC, to actually spend some money on 2D magnets and 2D magnetic research, how would you try to convince them?
Do I have to start?
This is a hard question, Marco?
That's a difficult question, yeah.
Yeah, I mean, you can always tell TSMC that you can make your transistor smaller and smaller, but then if you need a computer, so you need to also read and write memory. So how can you do this without solving this challenge?
I mean, I think we'll maybe leverage what Shimon say, and then like one answer will be, look, there is a limit until what conventional technology can achieve. So you have to research, you have to open on different opportunities, right? One of these opportunities for miniaturization and for fastest transistor and efficient memories is spin-orbit torque. There are others, yeah, of course there are others. If you look into how the 2D magnet has evolved, has been very fast, because a couple of years ago we thought they were impossible, then they made them, then in less than a year they made another one, and now it's been a couple of years, and now there is when I see now presentation, there is like 4 or 5 magnets in each presentation. So I think it's unbelievable how fast it's moving. There is a lot of money invested in from the fundamental point of view. So we're moving fast. So that means that there is something behind that. That means that it is interesting, and that means that we're making progress. So look at the progress, look at the time, and then it seems like very promising. So that's what I will say. Like, you have to do it, and this is a field that is moving fast. It's improving fast.
Yeah. And I would say, I mean, I have the impression that in general, if the materials are good, it's not very difficult to convince the industry guys, because I'm pretty sure these industry guys, they keep an eye on everything. So there are guys from the industry now most likely keeping an eye on these 2D magnets and everything that has been done. It's now under progress, and they're pretty good in identify the promising candidates. And I think if they identify, and then you convince them based on the fundamental work we do on the research. Of course you still have to convince them, but the properties that you get from the material itself will convince them, in the sense, okay, you build up this heterostructure, is delivering, is yielding great performance, or is new physics that leads to new functionalities. I think this will be enough to convince industry, and if it's good enough, I think they are gonna somehow manage to implement that in future technologies, right? Because this is needed, right?
Yeah, and I think that is an important point. I mean, we're going to need it in the future, and if we don't invest money now, in 10 years, 20 years from now, we hit a roadblock. And I think if we have to convince one of the companies, say, well, if you don't invest it, your competitor will, and then they will be ahead by 5 or 10 years. So I think that's Okay, and we've reached the end of the episode of today, so I would like to thank you for joining us today. So
thank you for inviting us.
Yeah, thank you.
Thank you, Mark.
And okay, then we see each other again soon.
Yeah.
Bye-bye.
Bye-bye.
Bye.